Hi, my name is Hanyu Chen, and this is my final project for 15463, Adaptive LiDAR Sampling based on Generalized winding numbers. First, I would like to introduce some background information. LiDAR stands for Light Detection and Ranging. It's a type of system that is usually used to obtain depth information for large-scale scenes. How it works is by sending a short laser pulse and recording the time lapse between the outgoing laser pulse and the detection of the reflected laser pulse. In this project, we consider a specific application of the LiDAR system to scanning a single 3D object and obtaining a point cloud representation of the object. The point cloud could be used for downstream tasks like surface reconstruction and rendering. So what is the problem we're trying to solve here? Most existing LiDAR systems scan the scene by directing laser pulses in a set of predetermined directions. Such systems do not adapt their sampling scheme to the observed scene, which means that a significant portion of samples might be wasted on rays that either do not intersect the object, or intersect the object in regions that we're already pretty certain about. Now, some more recent LiDAR designs allow them to rapidly scan the scene with programmable scanning patterns, and they could measure depth at arbitrary locations of the scene. And my project tries to leverage such LiDAR systems to progressively improve the quality of a 3D scan by adaptively adding samples in locations where the uncertainty in the object geometry is high. So how do we quantify this measure of uncertainty? Well, we could look at the related field of volume rendering, which have been used to model scattering media such as smoke and clouds. Recently, they have also been used to model opaque 3D objects. The main takeaway here is that in the case where you have a deterministic scene geometry and you consider a ray that shoots into the scene, the first intersection point of the ray is also deterministic. But if you consider the scene as a volume, the first intersection point is actually going to be a distribution. And if we look at how concentrated or spread out this distribution is, we get a rough idea of how certain we are about the scene geometry. So there are a couple related concepts here. The first one is the attenuation coefficient, or you could consider the discrete analogous concept of opacity, which is basically the proportion of light that is absorbed by the volume. There's also the transmittance, which is roughly the proportion of light that passes through the volume. The last one is the free flight distribution. This is the distribution of how far light travels into the volume before it terminates. And this is the most important quantity that we will be considering. Under a probabilistic view of the scene, we could consider an occupancy function which maps points in 3D space to the probability that the point lies within the object. So we know that the intersection of an object corresponds to locations where the occupancy is close to 1 and there is also a large change in the occupancy. Without going too much into the details, based on this intuition, we could basically convert the occupancy into attenuation coefficient values and ultimately into the free flight distribution that we use to quantify the uncertainty of a ray. Finally, how we actually measure the uncertainty in the free flight distribution is to compute its entropy. So a high entropy corresponds to high uncertainty in the ray. The remaining question is that, given a point cloud representation of the object, how do we convert it into an occupancy function? Well, we know that for a closed surface, the winding number measures the number of times a point is inside of the surface. We could extend this quantity to the continuous generalized winding number, which works also for point clouds. So the overall pipeline looks like this. Given a point cloud representation of the object, we adaptively find the next set of samples by casting random rays into the scene, determining the uncertainty of the rays, and keeping the rays with the highest uncertainty for the next LiDAR scan. An important note here is that these rays we cast into the scene are only simulations. They don't involve any physical process of sending or receiving laser pulses. For the experiments, we consider a baseline uniform sampler, which basically just samples n rays on a uniform grid. On the other hand, for the adaptive sampler, we sample n/4 initial rays on a uniform grid, and in each following iteration, we sample n/8 rays adaptively according to the method we just described. Finally, here are the quantitative and qualitative results on 4 different meshes. These results are obtained by running a surface reconstruction pipeline on the final point clouds, and we measured the chamfer distance between the reconstructed mesh and the ground truth mesh. We see that the adaptive sampler outperforms the uniform sampler across all 4 meshes and across different number of samples. We can also visualize the depth maps and the entropy values across different iterations, and we can see that the entropy values are indeed the highest in locations where there are no points. This is the end of my project. Thank you for listening.